So our speaker tonight is very well accomplished. He has had a tremendous career in business and in engineering. And he's been a radio amateur for a very long time. He's had a lot of experience. And our speaker also has given back to this hobby in many, many ways. One way is he has been writing a newsletter technical piece for years. And he has written on various subjects, and he is an expert on many of these subjects. I first ran into our speaker's books because they were available on Amazon, but I fixed that. They're also available at DX Engineering now. And his books are an accumulation of those newsletter articles that he wrote. And it's very down to earth and very understandable techniques about amateur radio, all sorts of tips and tricks and fun stuff. And so I got his books back in December, and I read them on a very long plane flight over to Germany. And I could not put those books down. They were so good that I bought one for my executive team at work and made sure they had volumes 1 and 2, and it was required reading for Corey and Scott Jones and the rest of the team. So I've just and I've gotten to know our speaker even better as time has gone on. And he taught at Contest University in May to a packed house. He had everybody in there just glued to the screen, and the information that he gave was great. And then I even asked him to present at Hamvention. He presented the Antenna Forum, again, a packed house. And so I am very pleased and proud to introduce Hal Kennedy, N4GG. And Hal, thank you so much for being here. He's coming to us from his home in Florida. And he gives the best NFED half-wave discussion I have ever heard. So I wanted to make sure that my home club got to hear Hal talk. Hal, take it away.
Yeah, wow, Tim, that's quite an introduction. I hope I can live up to 20 or 30% of what you just said. So such nice things about me. How's the audio sound? Am I Q5?
You're good here.
Good. Okay. Well, we'll jump into it. It's a pleasure to be here, and Tim, I really appreciate the invitation to speak. I enjoy speaking. When I noticed the date, I panicked a little bit because I've been asked to speak before to clubs the meeting before field day, and it tends to never go well. What happens is the field day conversation cranks up, and 3 hours later, everybody says, well, we're out of time, and we'll have our distinguished speaker come back next month. So kudos to the club for not doing that to me this time. That's always something funny that happens at the end of June. Let me see if I can make this work. By the way, I've been getting little warning indications here about limited bandwidth and unstable network, so I hope everything goes well. And let me see if we can make this work. Now, can you see the slides, or do you still see me?
We still see you.
Okay. It says now I am sharing. What do you see now? Still see me or see the slides?
We see your PowerPoint.
And
Okay, great.
put it in slideshow mode. There you go.
Yep, there we go. Okay, great. Well, this is kind of a favorite subject for a lot of people. The unfed half wave has become, I'd say in the last decade, probably the #1 most popular HF antenna on the air, and for many good reasons. With a simple piece of wire, you can achieve multiband or operate on many bands at once. And if you have room for a 132 footer, you can get 80 through 10 meters off a single piece of wire at low SWR with decent performance. And that's kind of unique to this design. There are very few antennas that can do something like that. We're doing it too with no moving parts, no traps, no stubs, no other unusual loading, coils or capacitors or anything. It's just a piece of wire with a matching transformer on the end. And the 80-meter ones will, in fact, give you 80, 40, 30, 20, 17, 15, 12, and 10-meter operation. So it's a great antenna for exploring and operating on all the HF bands with something that's very simple. They're easy to deploy. There's only one support necessary. You can hang them from the middle as an inverted V, or have one end, for example, in parks on the air, you could have one end on a picnic table and throw the other end up into a tree. So they're very portable for parks on the air or a vacation kind of QTH. Easy to put up, easy to take down. They're stealthy. They match with the matching transformers that come with these things directly to 50 ohms. And so you can directly feed them with 50 ohm coax and have low SWR. And they're fun. They're easy to make. You can make one yourself. You can buy one ready to go. There are kits available from the ARRL and other people if you want to roll your own, or you can buy the components quite readily and literally build one from scratch. So that's part of why it's everybody's favorite antenna for the last decade. This is just a quick snapshot of just two of the many store-bought ones that are available. MyAntennas.com is a well-known provider of these things. Par Electronics, under their trademark Par N4GG, sells a whole variety of these. Those are available from DX Engineering and Vibraplex. And in both of those cases, there are many models to choose from. There are ones for 80 through 10, 40 through 10, high power, low power, QRP, and so forth. So if you check the catalogs, online catalogs for these things, you can find many to choose from at different price points. The ARRL kit is a nice kit. It covers 40 through 10 meters. Easy to put together. There's very few components. It's really just a small amount of hardware and a toroidal core that you need to wind a transformer on. It comes with very good instructions. So it's really not problematic to build one yourself if you wish to. There's a few questions that come up about these things over and over again. And those include, what's the best physical configuration? You may only have one possible way to put yours up, horizontal or as an inverted V or an inverted L or so forth. And I'd certainly encourage you to put one up in any of those configurations. But under certain circumstances, there may be a best configuration. So if you have the opportunity to pick one, we'll take a look at what the best configurations might be. To get into that, I think we do need to spend a few minutes on how they work and what makes them work. So we'll start there. And then if you read up about them in any of the forums or the Facebook groups that are dedicated to these antennas, you'll see countless conversations going on about a counterpoise wire. Some people claiming you need one. There's at least a few manufacturers, unfortunately, that advertise their products and say no counterpoise required. That's not correct. And we'll spend a few minutes on counterpoises. And then these are mostly in use, I would say, at medium power with 100-watt kind of radios. And QRP would be second. But there are those of us who It's the only, actually, it's my antenna right now. It's the only antenna I can fit on my lot. And I occasionally like to run 1,000 watts. And so I'm going to spend a minute or two on how you can push these things power-wise up to the legal limit if that's something you really want to do. So let's jump into a quick look on how these things work. And this is a half wavelength of wire. And the orange line is the current in the wire, and the green dashed line is the voltage on the wire. If you don't remember anything else from tonight, remember what's down in the lower right-hand corner, which is that radiation from antennas, this applies to all antennas, is caused by the flow of current. So if you have something like a center-fed dipole, traditional half wavelength dipole, where the current peaks in the center of the antenna, the radiation is also coming primarily from the center of the antenna. And that's something you need to know if you're going to think about what configuration might I like the best. If you're going to hang one of these things up where the center of the antenna is close to the ground, it's not going to work as well as one where the center of the antenna is as high as you can get it. So knowing where the current is flowing is crucial, really, to understanding the performance of any antenna. And antenna guys, and I'm an antenna guy, tend to plot current along the antenna as opposed to voltage, because we like to know which piece of the antenna is doing the radiation. There's three opportunities. There's actually an infinite number of opportunities or locations you can feed a half wavelength wire, but there's three we tend to see and use. One is center fed. That would be a dipole. And typically, if the dipole is far enough up off the ground, it's going to show an impedance there of about 70 ohms, which makes a good match for 70 ohm coax or 50 ohm coax, typically fed through a 1-to-1 balun. You can move off center fed, however, and as you move away from the center of a half wavelength of wire, the impedance goes up and up. Off center fed to about the 1/3 point from the end will display an impedance of about 200 ohms. That's a nice place to feed the wire. 200 ohms is a very convenient number. A 4-to-1 balun will allow you to take 50 ohm coax to 200 ohms. And that's enough. That's a low enough impedance that the antenna will be stable. The feed point impedance will be relatively stable. And you can get multiband operation by feeding there, and we'll take a look at that in just a second. But you can move all the way out to the end. And out at the end of a half wavelength of wire, what we see is 2,000 to 3,000 ohms of impedance. The impedance is directly inversely proportional to the current. And you can think your way through that if you're comfortable with Ohm's law, just by using Ohm's law. For a given power, and I wrote that up here, for a given amount of power, the impedance is just proportional to the inversely to the current squared. So where we see high current, we see low impedance. That's right here in the middle, 70 ohms. And where we see very low current, we see very high impedance, 2,000 to 3,000 ohms typically. You can feed the wire out at the end, and that's what we do with a half wavelength antenna, fed and fed. But because the impedance is so high, we have a matching issue to deal with, and that is typically accomplished with a 49-to-1 transformer. It's possible to wind a transformer to give that impedance step-up ratio, and it will those transformers transform 50 ohms from coax up to 2,450 ohms. It's just 50 times 49, which will match the end of the wire. So you can get a good low SWR driving the end of the wire, driving 1/3 of the way out of the wire, or driving at the center of the wire. This does not affect the resonant frequency, by the way. And think about such an antenna the same way you would think about a guitar string. If you pluck the string in the middle, you get a certain tone, but if you pluck the string up at the top by the top of the neck or down at the bottom by the bridge, to get the same tone, It doesn't change. It gets more difficult to pluck the strings at the edges because the impedance, if you will, of that string is changing. And most of the sound, by the way, is coming out of the middle, just like this antenna. It's a really good analogy. The current's maximum in the wire in the middle. The vibrations are maximum in a guitar string in the middle. And that's where the radiation takes place. Let's take a look at the second harmonic. In this example, I've ditched the voltage curve because we don't really care about voltage. We really care about current. And it's the same orange line as before. The current peaks in the middle. But on the second harmonic, we get two current peaks, one about a third of the way out the wire and the other one about 2/3 of the way out the wire. And in the middle, we have a current minimum. This is why you cannot drive typically a dipole on its second harmonic. On the fundamental, it's going to look like 70 ohms, but on the second harmonic, where the current's almost zero, the impedance will be very high, back up to 2,000 to 4,000 ohms. There's a magical sort of sweet spot out here where whether the current is rising or falling as you move down the wire, it looks like 200 ohms on both bands. And so with a 4-to-1 transformer here, you can match this antenna on the fundamental frequency or the second harmonic. And out at the end where the current's always very low, you can match the antenna on the fundamental or the second harmonic because we have a stable impedance there to look at. It's 2,000 ohms in every case. Here it's 200 ohms in every case. Unfortunately, in the middle, it's not 70 ohms in every case. On some harmonics, it's low. It's a low impedance. On others, it's high. I'm going to test your patience now with the next chart. I consider this chart abuse of the audience. This is the black and white part is a chart that's been used on many other presentations by other people of N-fed half waves and was an attempt by N4GG to show all 8 harmonics, the fundamental and up to the 8th harmonic on a single chart. He elected for clarity purposes to put the odd harmonics below the antenna.
I'm here if you need anything else.
And the even harmonics above the antenna, but below or above doesn't really carry a significant meaning. You'll notice in every case, on every harmonic, the impedance at the end is always 2,000 to 4,000 ohms. So you can always drive this antenna from the end with a single matching transformer on the fundamental and all 8 harmonics, and you'll get a good match. However, notice also that if you try to drive the antenna in the middle, like a dipole, on the odd harmonics, the fundamental, the 3rd harmonic, the 5th harmonic, you'll see 72 ohms. But on the even harmonics, you're going to see 2,000 to 4,000 ohms. And so we don't have an antenna that's all band. We can't really have a network at the center of the antenna that's going to give us a match for 70 ohms and a match for 2,000 ohms. You got to pick one or the other. But here's this other sweet spot again, off-center fed. And it's a real eye chart and a real test. Please take my word for the fact that there's a point out there someplace where on every harmonic it looks like about 200 ohms. And that's why off-center fed dipoles work so well. Single 400 ohm matching or 200 ohm matching transformer will match the antenna on every band. Out here at the end, a single 49-to-1 matching transformer will match the antenna on every band. If you try to drive it in the middle, it doesn't work. All right, well, that's a bunch of technical stuff. And so what, right? What's that mean to me? Well, here's the good news. This is a typical SWR curve for an N-fed half wave, 132 footer, which should be resonant on its fundamental frequency on 80 meters. And here's the 2-to-1 SWR line. You can see on every band, we have SWR below 2-to-1. They tend to be a little high on 30, well, except for 30 meters. And they tend to be a little high depending on things in the terrain and the mounting location that may affect the impedance of the antenna to one degree or another. But usually you can tweak these in with the antenna tuner that's built into a typical rig these days. So frequently you can run them with no antenna tuner or with just a little tweaking of a small amount of antenna tuner. You got a great SWR. You can get them right down to 1-to-1. Okay, so what's the best orientation? We're finally up to the first question. How about horizontal, vertical, inverted V? Random? My first answer would be, if you only can do it one way, just go ahead and do it. In days gone by, a fellow named Lou McCoy, who was a very prolific writer for CQ and QST, used to say, look, all the RF has to go someplace. Just put the thing up. And that's my message also. Don't stress out too much about the best orientation. You may only have one choice. That choice is going to be good enough. The next thing I'd say, though, is the word best is ill-defined. It depends on what you want the antenna for. You want to have a rag chewing antenna for local and regional nets, for example, or and then, boy, there's a lot of nets on 40 sideband. You know, you might want the antenna for that. You might want the antenna to work DX or both. You may be interested in one band or many bands. You may be interested in portability. You may not. I had a Parks on the Air fella tell me, he says, my number one criteria is speed of deployment, which I would have never guessed. He said there are 8 parks I can put on the air from the coast of Georgia in one day, but only if I can put the antenna up and take it down in 10 minutes. So speed of deployment is a big deal to me. So if that matters to you, then we have to put that into the equation when we think about what's the best orientation. Some of the orientations are deployable in 10 minutes, some are not. Told park rangers don't like to see antennas in trees. So stealth matters usually. And if you have an HOA like I do, stealth matters. And then the orientation will affect noise level, safety. You can trip over these things. You can have high voltage on the ends of these things. And of course, what's available. You may have an opportunity to go high between some high trees. You may not, for example. So I'll give you the answer, and then I'll back the answer up with some charts. On the lowest bands, like 80 meters, almost all of your RF is going to go up no matter what. Don't stress out about what the right orientation is. Just put it up and have fun. This is an example of a 40 meter end-fed half wave operating on 40 at a height of 30 feet. This is the elevation plot. Notice most of the RF goes straight up. And this is the azimuth plot for the radiation. The antenna is vertical in this plot. And so most of the radiation is broadside to the wire. If you know anything about the radiation from a dipole, this is classic radiation. It's exactly the same as for a half wavelength of dipole. It doesn't matter that we're feeding it on the end. It could be fed 1/3 of the way out as an off-center fed. It would still have the exact same pattern. It's mostly being driven by height above the ground. And on 80 for sure, and probably on 40 meters, the radiation pattern is being dominated by height above the ground and will look something like this. And it doesn't matter how you put it up. You can put it up as an inverted V, it looks like this. You can put it up as an inverted L, it looks like this. You can put it up horizontally and it looks like this. So on the low bands, don't stress. And here's the radiation patterns for all the examples. Notice that the radiation for a horizontal wire, these are all 30 feet, or an inverted V, or an inverted L, or sloper, all look pretty much the same. All the RF's going up, pretty much up. I'm sorry, pretty much all the RF is going up, even more so in 80 meters, where as a fraction of a wavelength, you're going to be very close to the ground. The sloper has some directionality to it, so it's a little down in radiation off the back. compared to radiation off the front. But it's important to remember slopers don't have gain. Okay. You can't use it, you can't slope it to push a lot of gain in a given direction. You can slope the antenna to provide a small amount of nulling off the back. So if you had a noise source, let's say your house has a lot of noisy stuff in it, you could put a sloper sloping away from the house and null some of the noise out with a sloper. But the gain is going to be no better than if it was horizontal or an inverted V. They're all going to look about the same. So on 80 meters and 40 meters, don't worry about the orientation. It's not going to matter. Let's move all the way to the other end of the operating performance of these things up on 10 meters. Remember, I said the radiation occurs where the current occurs. This is the antenna wire. And on 10 meters, operating 10 meters on an 80 meter wire, you will have 8 current maximums. And here they are. And it's the interference pattern between those 8 current maximums that creates the antenna pattern. But they're not very predictable. If this thing's in the woods, the trees and the leaves will affect one or more of those current maximums. If this thing slopes at all, the ground will affect some of those peaks in current differently than others. And so my message on probably 12 and 10 meters, just like 80 meters, is don't sweat too much what orientation you use, because it's probably not going to matter. You're probably going to get what you get. The good news is that as we move up in frequency, the radiation pattern in elevation swings down. So now we're not pushing all the RF up. We're pushing all the RF towards the horizon. This makes it a good DX antenna on 10 and 12 meters, but it makes it a bad antenna for 10 meter net if you want trying to talk out 1, 2, or 300 miles. The other thing that happens when we move up in frequency is what used to be a broadside radiation pattern now moves along the wire. So the radiation tends to occur along the wire as opposed to broadsides of the wire. And it becomes more pronounced. And the longer you make the wire, any long wire antenna, in terms of how many wavelengths long, the more and more this happens. The more and more the radiation moves down towards the horizon, and the radiation occurs along the wire as opposed to broadsides of the wire. But this, especially in an end-fed half wave, is relatively unpredictable. These general trends happen, but you cannot count on a very specific pattern. Too many other things can interfere with the antenna that cause the actual performance to be, in some cases, significantly different than what an antenna modeling program might tell you. One more little technical item, and then we'll jump to some more mundane considerations. And that is, while these behave on their fundamental frequency just like a dipole, so if you're familiar with how dipoles work, these work the same way. They do not work the same on the second or subsequent even harmonics. If you operate a 40 meter end-fed, and this is a comparison, by the way, of operating on 20 meters on a 40 meter end-fed or a 20 meter end-fed. We're on the same band in both cases, but one antenna is twice as long as the other. The blue curve is the 20 meter end-fed operating on its fundamental frequency, which is 20 meters, and it's operating just like a dipole. On 40, though, there's this huge null straight up, which is somewhat unexpected. And most people never look at second harmonic operation because we can't feed dipoles in the middle and operate on the second harmonic. You can't do this with a dipole. You can't operate a 40 meter dipole on 20 and center feed it. The feed point impedance is 2 to 4,000 ohms, but you can certainly end feed it. When you do, the signal's coming down the wire, and I'm not going to go too deeply into it, but they tend to cancel the ground wave or the effect of the ground. And it turns into a very good compromise antenna for DXing and for local nets and shorter distances. So if you can, operate these antennas on their second harmonic if you're going to run end-fed. And you may, in fact, have that opportunity. It's if you're going to operate on 20 meters, it's much better to operate on a 40-meter end-fed on 20 than on a 20-meter end-fed on 20, because you'll get a significantly better radiation pattern. So let me take a sip of water. Here's the conclusions on the low bands like 80 and 40. Don't worry about it. Just put it up. All the RF's going to go someplace, and you're not going to be in control of that anyway. It's going to go straight up. On the highest bands like 10 and 12 meters, same story. You're not going to be able to control a radiation pattern very well. Put it up and have fun. On 20, 30, on 40, 30, 20, and 17, you do have control with the orientation. And my recommendation is go for the inverted L if you have a choice. It'll give you a good combination of some vertical polarization for DX work and some horizontal polarization for work around the United States. And that's a good mix. If you can't get an inverted L up, put one of the other ones up and just don't worry about it. Again, on 10 meters, you get what you get. On 80, it all goes straight up. Don't worry about orientation too much. A few more thoughts about your home station. Standard rules apply. Get it up as high as you can. An 80-meter one is really an ideal length. However, or an ideal antenna. However, they're 135 feet long, and you may not have room for it. You can dogleg these things all around your yard, and in fact, mine's not an inverted L, it's an L. I know people that have doglegged these things up and down trees and backwards and forwards around their yard, and they still work. So for your home station, the rest of what I said still applies. Inverted L is a good compromise. Slopers don't give you gain, but they give you some directionality. And a few more thoughts on orientation. Verticals are noisy, especially in urban and suburban locations, and they can be unsafe at the ground. We're going to look at the voltage on these things in a minute. It can be quite high. You don't want people touching the end of the antenna when it's in operation. And at a vertical, typically the high voltage ends at the ground. So that can be a consideration. Same for inverted Ls, the high voltage points at the ground. And you're going to need good insulators if you're going to run high power, because these things do have lots of voltage on them. If you're going to run high power, by the way, don't set the woods on fire. And people usually laugh when I say that, but I have experience, one my own and one a friend of mine who have done exactly that. Running 1,500 watts on antennas like this, they have actually started fires. So please be careful. Let's talk about the counterpoise for a moment. If you have a successfully operating end-fed half wave, you will have a counterpoise, whether you know it or not. You'll see advertising that says no counterpoise required. That's bogus. There's a rule of thumb, and if you're good at an antenna analysis, you can study that rule of thumb, or just accept the fact that that's a good rule of thumb. The rule of thumb typically is 0.05 wavelengths long is all you need, which means for an 80-meter wire, 13 to 14 feet is all you need for counterpoise. If yours is a 40-meter end-fed half wave, 7 feet's plenty. If it's a 20-meter end-fed half wave, 3 to 4 feet is fine. Don't overthink it. Don't get carried away. Just add that wire as a counterpoise to the location on the transformer box where it goes, and you'll be all set. That's all you need to do. If you don't supply a counterpoise wire, the shield of the coax will function as a counterpoise. The thing you don't want to do is have no counterpoise wire and put a common mode choke on the coax at the transformer. The common mode choke will stop current from going down the shield of the coax, so that can't be a counterpoise. And if there's no counterpoise wire, that can't be a counterpoise, and now you have none, and the antenna will not work. And people occasionally pop up on Facebook with that situation. You know, they say, gee, I've done a really great job. I put common mode chokes all over this thing, and I don't need a counterpoise because the advertising says I don't, and it doesn't work. How come? Reason why is you have no counterpoise. The counterpoise, a small one, a 13-footer, doesn't affect the radiation pattern. It's, again, back to what I said at the start. Radiation is caused by current flow. Here we are with the counterpoise at a very low current point in the antenna, so the counterpoise doesn't radiate much at all. So it doesn't affect the performance or the radiation pattern of the antenna much at all. So don't worry about the counterpoise much, but you do have to provide one. All right, quickly, how do we get to high power? Well, the medium power ones for sale typically carry this kind of a rating. A KW on sideband and CW and 250 watts digital. In pretty much every case, and I've done the analysis and some testing, you can push these things to 1.5 kW on CW and sideband, but you cannot push them any further than 250 watts on digital. And here's why. There are two problems in these things. This is one of the store-bought ones. And inside you'll find a little trimming capacitor and a toroidal transformer. On 80 meters, these transformers overheat. They tend to be inefficient as you go, more and more inefficient as you go down and down in frequency. So on 80 meters, if you run high power, they overheat. And the current through the capacitor goes up and up as frequency goes up and up. And so you will have amperes of current flowing through a very tiny capacitor on 10 meters. If you push these too hard on FT8, on 10 meters, you will smoke this capacitor. I've done it. And if you push these too hard on 80 meters, you'll overheat the core. And when that happens, the SWR goes pretty much to infinity. And I've certainly seen that happen. So what are we going to do? Well, if we want to run more power, let's talk about the capacitor quickly. There's plenty of options. You don't have to use the little rinky-dink capacitor that comes with these things. My current solution is to put 3 little capacitors in parallel. Here's the part number. These come from, they're made by TDK. They come from Mauser or DigiKey. They cost, in quantities of 1, 48 cents. Okay, so we're not investing money here to fix this problem. And in fact, I don't know why the commercial ones don't come with 3 of these in parallel. I mean, it's an extra $1. Gee whiz, why aren't they all that way? Anyhow, you can do that. That fixes it on 10 meters. You can also put in a doorknob. The manufacturers cannot do that because they retail for $20 to $30, but you can usually find them at a Hamfest for $2 or $3. So that's certainly a good way to go. And this is something I've been suggesting. I've never seen anybody do but myself, but you can put in an air variable capacitor. Again, it's cost prohibitive for a manufacturer, but you can buy one at a Hamfest. I bought a handful of these at the Dayton Hamfest for $2 a piece. This will take all the current you can throw at it, and you can adjust the SWR on 10 meters. If you install one of these, you can put this in to one of the store-bought ones, or if you make your own N-Fed half wave, you can use one of these instead of one of these or one of these. At any rate, don't use a single capacitor. Use 3 capacitors or a good doorknob or a variable, and you'll be all set. You have the 10-meter problem fixed. The 80-meter problem is a whole lot harder to fix. The typical N-Fed half wave comes supplied directly to you inside an oven, which traps in all the heat. This is thermally a bad design. There's a pressure relief valve that doesn't help you at all with air circulation. There's 2 tiny 1/8 inch drain holes in this thing to let moisture drain out, which don't help at all with air circulation. And there's no contact between the core or the windings in the box. So there's no conductive path to remove heat. So this thing's rated for a kilowatt on CW and 250 watts on FT8. And that's what you're going to get unless you do something to make this thing better, or you build one that's better. So let's take a look at what we could do. This is the very ugly result of many, many, many experiments. And what's been done to this poor transformer is the cores were held down to the box with zip ties. Heat sink compound was put between the cores and the box. The 1/8-inch holes were made unnecessary by 1 inch of air vents. And then there's another big air vent that was stuck in the back. And that's about as good as air circulation and conductive path heat dissipation as I could achieve in a store-bought N-fed half wave. And you kind of got to really tear into it. You got to be willing to, to get your pliers out and really start hacking away at these things if you want to do that. And even that doesn't really solve the problem on 80 meters. As that thing came to me from the factory at 500 watts, which is double the rating, it would overheat in 13 minutes. After I added the heatsink compound, the zip ties, the soffit vents, the extra holes, and all the rest of that stuff, I got it up to 18 minutes, which is almost a 40% improvement, but it's still 18 minutes. So if you want to run 500 watts on FT8 with one of these things, after about 18 minutes, you're going to have to stop and let the thing cool off. And kind of indicative of just where we're really standing is even with the cover off, which is as good as it could possibly get, it still overheats in 22 minutes. So there is a way though. I mean, and if you're really intent on running high power on FT8 on 80 meters, you can make some of these changes. But better yet will be to do the right thing. So in conclusion on that subject, from 40 through 15, usually not a problem. You can really push the power. On 12 and 10 meters, if you change the capacitor, you can really push the power. On 80 meters for RIDI and FT8, even with thermal management, the store-bought ones are only good for 15 to 20 minutes of operation before they overheat. But you can buy and you can build special ones that will take all the power. They're expensive. Instead of 2 cores, they use 3 cores, ferrite cores. The ferrite mix is a different mix, which is more expensive mix. They run them hot. The standard mix starts to fail at 130 centigrade. This more expensive mix fails at 250 centigrade, and they run them up there. And you need a different box, by the way. The boxes we tend to use, NEMA boxes. If you're building your own, you get a NEMA box at Home Depot. That's made of PVC. That box will melt at 200 centigrade. And you may want to be running up around 250. So you need a polycarbonate box. On the internet, you can find polycarbonate boxes. But now we're talking about a device that's going to cost about 3 times as much money when you're all done. So can you run 1500 watts on FT8 if you think that's a good idea? And of course, a lot of people think that's a terrible idea. But if you really want to, you're going to need to go this route. You're going to need to go to more cores, better cores, and a better box. Very quickly, what's in the market and what can you get? And I mentioned this in the beginning. MyAntennas.com makes a whole bunch of them. Power N-Fed makes a bunch of them. QRPguys.com makes really nice small ones. There are many, 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 many other people making these things. The ARRL kit covers 40 through 10. It's a fun kit to put together. It's a company called HF Kits. They have a very similar kit. If you want to really start rolling your own, DX Engineering, Palomar, and Ballum Designs and others sell just the transformer box or parts. And Mauser, DigiKey, and DX Engineering sell just the core. So if you really want to go from scratch, you can buy the pieces and parts from scratch. And it's not hard to do. There are a bunch of cores for sale on Temu, Alabama, and Amazon. Please do not buy them. A lot of them have cracks. A lot of them have voids. The price reflects the quality. They're terrible. I don't know if you're going to have access to these charts after this presentation, and I'm just about ready to wrap it up here. But there are 2 wonderful presentations on the internet. They both have the same title, The N-Fed Half-Wave Antenna, by Steve Dick and by Steve Yates. You can do a Google search on K1RF or AA5TB, you can find them, or N4LQ, and you'll find Steve Ellington's stuff. very, very, very good, more detailed information than I'm providing tonight. Ferrite, who makes the cores, has some excellent technical papers, as does Palomar Engineering, and those are on the internet. And then Facebook. There, at last look, there were 53,000 members in the NFED Halfway Facebook group. I would say 50% of what you're going to see there is wrong. Lots of opinions, lots of attitude, lots of back and forth and up and down. Sometimes very good information, sometimes very bad information. Use your judgment. It's the internet. Use your judgment. It's the internet. And that concludes my comments. I'm happy for questions if you have time. This is very similar, as Tim mentioned, and usually I don't plug the books, but the way I talk is the way I write. And if you enjoyed any of this material at this level, presented this way, is in the books. So if you want to hear more or see more, they're for sale on DX Engineering and Amazon. And I hope we had good internet all the way through, and thank you very much.
Thank you, Hal. That was great. Does anybody have any questions for Hal? Well, imagine that.
Yes.
Dave, go ahead.
Al, you mentioned slopers. I was always under the impression a sloper had gain toward the forward. That's not true, but you say it does have selectivity and eliminate noise from the rim. Is that correct?
Yes, although I fudged a little. It's very dependent on frequency. On the fundamental frequency, like an 80-meter sloper on 80 meters, you will see virtually no gain off the front compared to, say, a dipole. You'll see some null off the back. But as you move up in frequency, if you're running 20 meters on an 80-meter NFED or 15 meters on an 80-meter NFED, you will see some gain off the front. Not a lot, but you will see some gain off the front. Part of what's killing the gain is proximity to the ground. On 80 meters, you're typically so close to you're typically a tenth of a wavelength or 2/10 of a wavelength above the ground. And the ground is loading the antenna to such a degree that it's very hard to get any gain from any configuration. So that's the reason.
So then sloping the 75-meter dipole is not going to help if you want to get any directivity.
Not much, no. You'll get a better signal to noise ratio if you put the noise to the back of the antenna. By the way, be careful about which way it slopes. If the low side is at your feet and the high side is at a distant tree, so it's sloping up away from you, the gain is to your back and the null is to your front.
Okay, yeah, that would be a misconception. I definitely have.
Right. We like to think the direction the thing is going up must be the way the gain is going up. And it's the opposite. That's where the null is. The gain is actually off the back. What a lot of people think of as the back.
All right, David.
He could go on all night, and if I would let him, he would. We love him. Anybody else have a question for Hal?
Just a small suggestion. Yeah, you're trying to get rid of some heat at 80 meters. I have one idea that might work. And that would be to use the same type of TEC device they use to do the coolers, the solid state coolers they make. It's two pieces of metal that are joined together, and you have to put electricity to it to go and make one end cold and the other end hot, and use a fan to take that heat away. So
Right.
Get some more cooling off that core.
Yeah. Seems like a good idea. The problem is these transformers are terribly detuned by nearby metal. The reason I didn't suggest a metal heat, I'd like to put a metal heat sink, just grab a metal heat sink and stick it on there. As you get a metal heat sink close to the transformer, it detunes the transformer pretty significantly and they don't work right. And I think that would happen for one of those heat transfer or for one of those thermal electric generators also. They're basically metal. And if you're going to bond it against or close to that transformer is going to detune the transformer. Sadly, because I'd love to find an answer for this. I looked into non-conductive heat sinks, and there are companies that make heat sinks out of alumina, typically put on top of CPU chips and computers, but they're very tiny and they're relatively expensive. And if you want one big enough to put on a 2.4-inch core in one of these transformers, number one, I can't find one that big. And number two, if someone made one that big, it's going to cost a bunch of money. So I'm still looking for a non-conductive, electrically non-conductive, conductive heatsink.
And you don't want to plug in something to the feed point of an antenna. That would be.
Right.
Yeah, that's.
I was gonna say, since you mentioned that the cores do detune, and when you get close to metal, you wouldn't want to have this mounted right against your aluminum siding either.
Matt,
You had mentioned overheat times on 80 meter. Now that's just if you're transmitting, right? You can listen infinitely without overheating anything.
Yeah, that's a great question. First off, sure, you can listen forever and it won't overheat. The average power, those numbers were for continuous operation on FT8. But FT8, the average power at FT8 is 42% of the carrier power. So, excuse me, so if you're running 1,000 watts, the average power is 420 watts. Those experiments were done at 500 watts, so the average power is 42% of that, something like 200. And that's the way to look at it. Meanwhile, that's sort of bad news, isn't it? Because even at 42% of average power at half a kilowatt, you're on the edge of the thing not being able to operate steady state on and on and on and on. You can make contacts for 15 to 20 minutes on 80 meters and then let it cool off for a while. Yeah, that's taking into account the duty cycle, which is actually a little bit less than 50%. In the FT8 waveform, you transmit for about 12 seconds, you listen for 17, you transmit for 12, you listen for 17. Doing that continuously, just continuously, one contact after another, after another, after another. That's 42% duty cycle. Yeah.
all right. Anybody else? Hal,
Good
thank
question.
you. Hal, thank you so much. We really appreciate you speaking to our club. And this was recorded, so Corey will have it up on our website. It'll be on YouTube. And if you forget, all you have to do is go to YouTube and put in Mercer County Amateur Radio Club, and we come right up.
Or if you go to the website, there's a link on the left side for the YouTube channel.
Yep. So it's real easy. You can watch this again. You can tell others about this presentation. And Hal, we wish you the best, and we hope you have a great summer. And thank you for being here.
Great. Well, thanks, Tim. It's really been my pleasure. Always great to get some good questions. So I'm very appreciative of your time. Thanks.
All right, let's go out and have some fun on field day.
Yeah.
And Mike, you're up with your